Okay, here is example 2.25, logistic equation. And actually, this one is very, very similar to our last one for a falling object. And just in that it requires partial fractions to do it. So they start with du dt, and really this section, they are just going through the algebraic process of solving this. And so it's really, once you separate the variables, it is really a review of Calculus 2 techniques. Okay, so we're going to leave the r on the right hand side, and we'll go straight to our du over u times 1 minus u over k equals the antiderivative of r dt. Okay, so again, the right hand side's a piece of cake. But what we have to do for the left hand side is we want to write 1 over u times 1 minus u over k as an a over u plus a b over 1 minus u over k. And what we need are two equations, two unknowns, and you can come by those a couple different ways. Now I'll let you review your Calculus 2, or you can always talk to me about reviewing Calculus 2. But my way is to typically choose particular values that make life a little bit easier when you, if you now get a common denominator, right? You get 1 equals a times 1 minus u over k plus bu. So you see, I found a common denominator, but I'm just looking at the numerators. And here is some voodoo math that actually works. Okay, it's voodoo math because if all I'm doing is looking at the numerators and doing this, it's really not the best idea to go about this. Oh, let me pause it for a second. Just a minute. Okay, I'm back. So as I was saying, you want to choose judicious values for u here. So notice if I let u equal 1, what happens is then wait, u equal, no, I'm sorry, u equals 0. That's what I wanted. U equal 1 would be a bad value. U equals 0, then notice what happens. I get the equation 1 equals a times 1 minus u, 0 over k, because I let u be 0. But that got rid of the b. And so we end up with a equals 1. Awesome. Now, the reason that's voodoo math is if I let u equal 0, I'm actually back here, dividing by 0 there and there. So, it's voodoo, but it actually works. And so then I'll do the same sort of thing to zero out a. I'll say, oh, well, let u equal k. And if I do that, then I'll get 1 equals b times k, or in other words, b equals 1 over k. And those do indeed work. And so what I have is that 1 over u times 1 minus u over k can be written as 1 over u plus 1 over k times, or divided by 1 minus u over k. So I can do that. Now, actually, if I take the k down to the bottom here and multiply through, I guess I can write this as they do, 1 over u plus 1 over k minus u. Okay, so now I know that that is written that way, so that's that partial fractions thing. So what we now know is instead of integrating that, I can integrate 1 over u plus 1 over k minus u du, and that equals r, well, I can put it on the inside or the outside, but r dt. Okay, well, so we get a natural log of the absolute value of u. Okay, so that's that one. Plus, in the case of the k minus u, that will be, when you do that by substitution, you'll get actually a minus. So minus natural log of the absolute value of k minus u equals rt plus c. But just like, in the previous example where they had the one logarithm over the other, this is a minus, so I can write this as a single logarithm and write it as the absolute value of u over k minus u equals rt plus c. And of course, then I can exponentiate both sides, do the u over k minus u in absolute values, e to the rt plus c, but now I can call that, I'll put it over here, I guess, c1 e to the rt. I'll even put the little positive thing on there. And so then u over k minus u is equal to plus or minus c1 plus e to the rt. Okay, so we have that same thing. But again, as before, we can now drop the plus minus, saying, well, we've got this arbitrary c. So I'll say u over k minus u is equal to c2 e to the rt. And then again, well, multiply both sides by k minus u, distribute, let's see, if we do that, we get u, and we'll have 1 plus c2 e to the rt. On the left-hand side, we'll be left with the equals k c2 e to the rt on the right-hand side. So u is equal to k c2 e to the rt over 1 plus c2 e to the rt. Okay. And they say, oh, finally solve this last equation and get something similar to what they have. Okay, well, where the heck what did they do? Well, let's factor out this out of the top and bottom. And if I do that, I get, they'll cancel out, but I get a k here. Now, I'm going to get a 1 here because I factored that out. So I'm going to put that 1 there, and then plus multiplicative inverse of this, which is 1 over C2 e to the negative RT. And so I get that, but then they say, oh, well, a constant's a constant, and so K over 1 plus C3 e to the negative RT, and so they get their solution that looks like that. And you can do the initial condition, you know, u of 0 equals u0, but u of 0 would be K over 1 plus C3, and so we can get what, C1 plus C3 is equal to K over U0, and so C3 is equal to K over U0 minus 1. And so we could fit that all in there. They do that. And rewrite everything as u of t is equal to, now they move some things around. I'm not going to bother with that. You know, I mean, I'm just going to go with their solution. You can play with that one. K times u0, u0 plus e to the negative RT times K minus u0. Okay, so that's how they make it look when they substitute that in and play with it a little bit. All right, so that is that idea of separable equations. Certainly you don't always get partial fractions, but you often get partial fractions. Now, you should work on that sort of thing. You know, the algebra is a good technique and so forth. But at the same time, you know, once you've separated the variables and you need to do the antiderivatives, well, you know, get the antiderivatives done any way you can. And, you know, there are many ways to do it. I will probably make a video showing it using a Sage cell, because I think it's good to learn the Sage cell stuff, partly because a lot of it's based on Python. So, all right, that does that one. Whoops, let's see, I gotta go to the right place to stop it here.